coming to the workshop. So today I'm going to share with you things we do at Alibaba. So follow Andy's talk in the morning. So we are embarking on a journey to what we call SDDP. SDDP stands for Self-Driving Database Platform. And in my talk, I will share with you our experiences and one example problem that we have tackled in this journey. So here is the outline of my talk. So first of all, I'll give you the background of this work. So at Alibaba, so here are the challenges for Alibaba's database team. So we provide database infrastructure for greater than 100 business units. They range from e-commerce, well-known like Taobao and Tmall, something similar to Amazon.com. And we also have Alibaba, which is something similar to Uber Eats. And we also have a map service, something similar to Google Map. So and we also have Cainiao Logistic Network, which is responsible for packaging and delivering and things like that. Okay, so as you can tell, so the business operations are fairly complex and complicated at Alibaba Group. And being the database infrastructure for those complex operations, of course, raise a lot of demands. And over the last, 10 years or so the scale we are looking at has grown dramatically. So in fact, if you look at the number of database instances that we manage, in the last few years has exploded by more than 1,000 times the number of instances of database that we manage in our team. So in addition to all the operations at Alibaba, within Alibaba Group, we also provide services to different customers from different sectors on Alibaba Cloud. So this raises a lot of challenges for availability, security, stability, scalability, performance, and things like that. At the same time, the company, of course, as with any other organization, asks us to significantly downsize our DBA team, database administrator team. In fact, at the moment, as we speak, to manage all these complex operations, my team has less than 50 DBAs to manage a complex environment as such. So how we manage to do this? Of course, machine learning is a big part of it. Machine learning is really at the core of the reason why we can downsize our DBA team while the business complexity has grown to the roof. So to summarize what I have just mentioned, here is the database usage within Alibaba Group internally. The business is divided into 3 different groups: digital media and entertainment, core e-commerce, and then local services, such as map and things like that. Then at the infrastructure level, mainly is provided by Alibaba Cloud. In other words, customers on Alibaba Cloud are using the same infrastructure that our group is using internally. So they actually are seeing and using the same technology. So all of this give us the numbers down below. It's huge, of course. And I'll give you one example of the technical challenge that we have to tackle. So here is a Singles Day, which is a well-known shopping festival in China, and increasingly it becomes famous outside China as well. So Singles Day is, the name comes from the date that this shopping festival is executed. So annually on November 11th, so there are 4 ones, and in Chinese, one means single, right? You are by yourself. So that's why the name is called Singles Day. Okay, on Singles Day, there's basically the big promotion going on for the entire day. However, a lot of items that are on sale will be grabbed by the customer very quickly at the beginning of that shopping festival, which starts at the midnight of the November 11th, meaning that when time grows from November 10th, the midnight of that, to the first second of November 11th, there is a huge increase in demand coming to our e-commerce website. How huge the increase of the demand is? Well, look at this graph. So in 1 second, by the way, the y-axis is transaction per second. X-axis is time in minutes and second level. And I hide the numbers so that we can focus on the scale we are talking about. So it is the spike in terms of transaction per second to our database system grow more than 122 times in just 1 second. And we had a paper in Sigma this year, Sigma 2019, highlighted the system challenge that we have to tackle to address this. If you're interested, I refer you to that paper. The title of the paper is called X Engine, which is a storage engine for a transaction database system we have designed to tackle this. So here is a collection of sample of customers on our public cloud. As you can tell, really the reason I put up this slide is not to do an advertisement for Alibaba Cloud, rather to tell you the background of the customers on our cloud infrastructure is super diverse. What that means is you really need to customize and customize tuning performance of your database system for different applications from different backgrounds, from finance, from retailer, and so on and so forth. Okay, so to summarize the few slides I've just gone through, so essentially what we are looking for, we're looking at management at scale. We want to do smart scheduling, smart protection, smart runtime management, optimization, backup, restore, security. All these issues, we want to see how we can leverage machine learning and AI technologies to automate this. And then we also have to look at some of the traditional system challenges, such as scalability, stability, and cost. The super hotspot I just mentioned from single thing. Then, at the same time, we also need to be considerate to the fact that we have really diverse workloads. And in all of this, especially for our cloud customers, we need to guarantee a predefined service level agreement that we have signed a contract with the customer. So that's essentially the challenge we face. So here is a little bit of history of how we dealt with that at Alibaba. So in the early days, up until 2010, so Alibaba's database infrastructure relies mostly on commercial database systems. In particular, we were relying 100% on Oracle until up to 2010. Then at the time, there were a lot of DBAs involved. In fact, in the old days, of course, I joined Alibaba early last year, but when I talked to members of my team who were from those days, they told me back then the database team at Alibaba essentially is simply a group of DBAs. That's the entire database team, nobody else. All of them are DBAs, and furthermore, they are DBAs specialized in only Oracle. So if you know how to tune Oracle and you can tune Oracle to its perfection, you were literally a god back then at Alibaba, because all business units want to talk to you, how to tune Oracle to get the best performance out of it. Then in 2010 to 2017, the group decided to switch from Oracle to open source database system. In particular, they've been using MySQL for the most part. And in the journey of that, they enhanced MySQL and did a lot of patch to the kernel and so on and so forth. There's a version called AliSQL they've been using. Then in 2017, up to now, basically around the time I joined, we started building cloud-native database system. In particular, there are two products and two systems we've been building since then. One is called PolarDB, which is something very similar to AWS Aurora. And there's another system called AnalyticDB, which is something very similar to Redshift. So now let me talk about SDDP. Self-driving database platform, we define it as these four key dimensions. First of all, we want the system to be self-tuning. Then we want the system to be self-securing. Then we want the system to have the capability of doing self-detection and self-repairing. And in the core of it is what we call self-decision making. So this is really directly derived from the challenges I have mentioned, such as database diversity, self-driving capabilities, and so on and so forth. So this is really to replace this DB PaaS, database platform as a service, to what we call a self-driving database platform. So here is an overview of the rationale behind this. Essentially, we collect a lot of data. We collect a lot of performance data, workflow data in real time. This is like eyes of a human. Then we use machine learning at the core, which is like brain of human. Then the execution, we call it also automation, is like hands and feet. Then of course there's the feedback loop. So then we intimate a self-driving database platform to self-driving cars. If you follow a little bit of what's happening in that universe, in the self-driving car universe, they have this so-called different levels: level 0, level 1, level 2, level 4, level 3, and level 4. Level 4 is essentially 100% self-driving car. Level 0 is no self-driving capability at all, like human is a driver. So we take that and we similarly define different levels of what we want our self-driving database platform to be. So currently, we are in the process of moving from level 2 to level 3. Level 2 is a single point automation, meaning that there's a specific component or algorithm you have used AI to some degree. That's what we call single point automation. And we are upgrading our system to partial scenario automation, meaning that for the most part, our system runs on SDDP, but we still need human intervention. So that's where we are at. So some of the key features in this space is like automatic SQL tuning, automatic configuration tuning, auto-scaling, resource scheduling, and so on and so forth. Okay, I will mention some of those. And here is a big picture showing what I'm talking about, right? Tuning, optimized SQL, config optimization, auto-admin, anomaly detection, protection, security aspect of SDDP, elasticity. In the cloud database age, elasticity is super critical, right? Decoupling of storage and computation, the core principle behind the design of Aurora is to go for better elasticity, right? Then operation, right? So the management of resources and so on and so forth. So some of the projects we've been working on, I'll give you some examples. First of all is knob tuning. This is follow the seminal work by Andy, right? Auto-tune, right? So we've been using that idea and of course doing enhancement to that, try to do knob tuning in our systems. Then another project we are doing right now is what we call hot code separation. So in a lot of database systems nowadays, you use LSM tree structure, like in RockDB and LevelDB. And in that case, we want to be able to figure out what's hot item, what's cold item, and using machine learning to do that. And then there's another product we call Cloud Bench. In our opinion, TPCC, TPCH, and even Sysbench, they are great, they are wonderful, but they do not necessarily capture the characteristic of database workload at the cloud infrastructure. So we're trying to use machine learning technique to build a benchmark that can generate database workloads that are similar to real cloud environment that the community can benefit from. Then we are doing, of course, using SDDP to do anomaly detection. And then another project is called natural language to SQL, right? You can ask a question in natural language and automatically translate it into SQL. Then design recommendation of this follow the exciting work, I think it's the last year or the year before last year, things like Learn Index, right? That generate a lot of interesting quote-unquote conversation in the community, right? So of course, obviously, I don't have time to go over all of this today. So today, I will dive into one specific problem because I think I've given you enough background and overview. Now, from 10,000 feet, now I will dive all the way to the ground and give you one problem that we have solved. And we actually had a paper in WellDB this year, so you can learn more about that in that talk. But today I will try to give you the key idea of that work. And not only it leads to a research paper at WellDB, it's actually been deployed at our production system. I will tell you what's the effect of that. And this work is from this space, knob tuning space. So what specific knob tuning we're doing? So this product is called IBTune, individualized buffer tuning. So the motivation is as follows, right? So this is our platform, self-driving database platform, and then you have applications from different business domains like Tmall, Dingding, and Hema. Dingding is something similar to WhatsApp, okay? And Tmall is like e-commerce, like Amazon.com. And Hema is offline shopping mall kind of application. Okay, so you have databases for those different applications, and what we're interested at tuning, we're interested at tuning the buffer pool size of those database instances. Why? If you look at the table down below, we look at our memory consumption for our infrastructure. We quickly realize the buffer pool of these database instances is actually consuming the most significant part of our resources. In fact, they take more than 99% of our total memory consumption. Average buffer size for an instance in our business application is about 29 gigabytes. They are other buffer consumptions, memory consumptions, are dwarfed by this. So we're really interested at tuning the size of this buffer of each individual database instance using machine learning algorithms. So this is the overall picture, right? So we collect performance metric and knobs values in real time and build a model and tune and using a feedback loop to do that. So this is the overview of what we have done. And I can tell you the end results. Currently, we have deployed this IBTune component in our production system and managing over 10,000 instances. We haven't scaled out to all instances yet because we still want to have some time to verify this actually works. So we currently deploy this over 10,000 instances, and it results on a daily, on average, on a daily basis, save our memory consumption by over 20 terabytes, which of course is significant. So what's the motivation? Why I want to do this? If you look at the right curve here, the right curve shows you before this project, our DBAs will use those values to set the buffer size for a particular database instance. How many values they are actually using? They're only using 10 values. They're only using 10 values. So the buffer size, this is by the way in gigabytes. So it's either 1 gigabyte, 2 gigabytes, 8 gigabytes, 20, 45, some whatever values they randomly come up with. So over the hundreds of thousands of instances we manage, we're only using 10 different configuration values for those instances. Okay, point number one. Point number two, once the instance is set to a particular value, rarely it gets updated. It's used as a constant over time until something really bad happens. What we want to do, motivation number one, is to come up with a blue curve like this so that you can set the buffer size of an individual instance in a continuous domain. You can use whatever value you want. Secondly, you can adjust this back and forth, up and down in real time, subject to the workload and the response time requirement. So of course, the key of doing this is to make sure while you are adjusting your buffer size, you do not negatively impact the response time of your query workloads going to that instance, right? For example, if your buffer size is at 64 gigabytes, now you downsize that to 16 gigabytes. Fine, you end up saving a lot of memory, but if as a result of that, your response time skyrocketing, then the business application will complain to you, right? The service level agreement will be breached. So what we want to do is, okay, you want to tune the buffer size, but in a way that the response time, of course the response time will be negatively affected. However, we want to make sure that it's not super negatively affected, so that it's still within the level of SLA that we promise to the end users. Okay, so that's essentially the idea. And the response time, furthermore, we identify the correlation between response time and the buffer hit ratio. So at the end of the day, what we're really tuning is the relationship between buffer size and the hit ratio of the buffer. Because we notice that buffer ratio directly determines the query response time, for the most part, unless it's a CPU intensive workload. For the most part, a lot of database workloads are not CPU intensive, they are IO intensive. So this is really the relationship. That's why we show also the figure of CPU usage. As we see, tuning the buffer size has little impact to the CPU usage. Okay. So so that's the high level idea. Then how do we identify the relationship between buffer size and hit ratio? That's question number one. Question number two, then once you know the relationship between hit ratio and buffer size, how do you then determine the relationship between hit ratio and the response time of that instance? We need these two models. Once we have these two models, then we can plug this into our production system and let it play, right? So that's essentially the idea. So for these two problems, we come up with two functions or two models we are trying to tune. One is a function that the input is a miss ratio, the output is buffer size. So we want to identify the relationship between buffer size and hit ratio. And then the another function takes the hit ratio as input and produce the response time as output. With these two functions, we can then use this loop to tune the size of our instance. Okay, so that's the high-level idea. Okay, and next I will show you how we build these two functions. Function number one, how do we find the relationship between buffer size and miss ratio? So this actually we did a large number of experiments. We get this curve right here. So the blue curve is a real value. The red curve is the linear fitting of that curve. So we did tons of experiments. We actually found out there's a relationship like this. BP target stands for buffer pool size of your target size and buffer pool size of current size. And then the miss ratio of the target size, if you set your instance to that size, and the miss ratio of the current size. We figure out they actually follow a power law distribution relationship like this. Okay? Of course, this is heuristic, right? There's really no theoretical, fundamental theoretical guarantee to it. But in the paper, we actually analyze the mathematical model behind this and why this is a good heuristic for most database workloads. Okay. Then with this functionality, the next thing we do is we want to find a so-called tolerable miss ratio. So how do we do this? Is we use the idea of nearest neighbors. Essentially, the idea is, okay, how do I, given an instance, right? How do I find other instances that behave similar to this instance, so that when I change the buffer pool size, they're gonna behave similarly to those other instances with similar setup, right? So the idea is to use nearest neighbor to do this. So there's no trick here. Essentially, we map all instances to a high-dimensional space. Then we find nearest neighbors. Those are the basis of tuning the buffer size and the hit ratio. What metric we're using? We're looking at those metrics: response time, query per second, miss ratio, CPU, logical rate, and I/O rate. I/O rate in our case, by the way, we use direct I/O, so each I/O rate represents a real I/O to disk. So we use all of this, and of course we normalize all this metric against query per second, QPS. Okay, so this put out each instance to a high-dimensional space. Then we can then use this to find instances with similar configurations and similar hit ratios using this nearest neighbor strategy. Okay, so that's essentially the idea. And this allows us to calculate the new buffer pool size given a target hit ratio. Okay, given a target hit ratio, using this nearest neighbor trick and also that function model we have talked about just now, we can calculate the new target buffer size. Okay, so that's step number. That solves this problem. Next, we want to solve the second problem, right? Now, given this new buffer size, now with new buffer size and new predicted hit ratio, what's the relationship between that hit ratio and the response time? To do this, we use a pairwise deep neural network to do that. The idea is, for all the instances we have, we group them into pair. So every two instances is in a group. Then we put them into a pairwise neural network like this to predict response time based on a tolerable miss ratio. The idea is we input two instance metric plus one instance's response time in the training stage. Then the training objective is to figure out the other instance's response time, which we do. We have the value for that. That's why we can do this training. But we purposely omit it from the input, from the left-hand side. And we use this to train this network to figure out, okay, if the two instances, the metric are like this, like such, and one instance we know the response time, the other we don't, how can you predict the response time of the other one? We built a network to do this. Okay, that's our training stage. And then at the runtime, what do? We take one instance. We take one instance as the input. Okay, but one with the current configuration, one with its target configuration, the target buffer pool size. Okay, with the current instance, we know its bit ratio, but with the target buffer pool size, we know the hit ratio, but we do not know the response time. But with the network we have trained, once you plug them into the network like such, magically a prediction will come out, which will be the predicted response time given that hit ratio and given that buffer pool size and all the metric setting for that instance. Because that's what the network is trying to do. Then we use this as our prediction, and then we simply plug this into this loop to see whether the predicted response time is within a safe response level threshold with regard to our service level agreement for that application. A key important highlight here is that while we do this prediction, we are only changing the buffer pool size while the other metrics stay relatively stable, right? The QPS, the workload, and all the other things, because we don't expect that to change in a level of just a few minutes, right? So what's a safe, and when we talk about comparing our prediction against the service level agreement, how do we figure out what's the right threshold to use? And we run a lot of workload with regard to different applications. We typically find that if you use the response time and all the other metric in the history, if you do a PDF over those, you take the 95% quantile out of that. That's typically a very safe threshold that customer will be satisfied. So that's what we use over there. Okay. Next, we look at deployment and results. So those are some of the key ideas. Of course, I omit a lot of details, which I encourage you to go to our research talk. I don't know which day it is. Maybe it's on Wednesday. Okay. So here is the overall system. That's what it looks like. On each instance, we deploy an agent, collect those metric data I talked about. Then you go through a streaming processing system like Kafka. Then build a network training, and then there are really two models I mentioned. One is the buffer pool size relationship with hit ratio, then hit ratio with response time. Then we do the scheduling and execution. And there's one last missing piece I need to talk about, which is, okay, now you have an instance, now you have those two models, you know how to tune the buffer pool size so that the new response time will be still within your service level agreement, and hopefully your new buffer pool size is smaller than the current one you're using, so you end up saving memory. So that's an objective. But when you do that tuning, when you tune the buffer size in real time, the performance application running on the instance will inevitably be affected. However, a lot of mission critical applications, they do not want to see any impact whatsoever to their application, unless you are sure changing this buffer pool size will not negatively affect their application. Meaning, after changing to the new buffer pool size, service level agreement is still satisfied. What if your prediction is wrong? You change the buffer pool size, service level agreement is breached. What do? Then that's a really bad scenario we want to avoid. We cannot afford to have this. Even a single case, we cannot afford to have this. So how do we do this? So the idea is, we are using a protocol called XPaxos, which is a variation of Paxos to guarantee high availability anyway. So all of our instances are three-way replicated anyway. Of course, by the way, XPaxos does not replicate raw data, it replicates the bin log of the system so that the replication cost is really, really low. Of course, I don't have time to go over the detail of that, but the idea is you're gonna have a master and a backup running all the time. And we do not adjust the master buffer pool size in real time. Instead, whenever the model tells us to do something, we adjust the buffer pool size of the backup node, which is synchronized with the master node at all time using XPaxos. Then we wait for about 10-20 seconds for that backup node to be stabilized with the new buffer pool size. Only then we switch the master and the backup node. Now, remember, the backup node becomes the master and the master becomes the backup. The critical observation is, while you do this, the old master, which is the new backup node, still has the old configuration. So if something goes wrong, you have something to fall back to. And at all times, these two the new master now the old master now the new backup, and the old backup now the new master are still synchronized using X factors at all times through the bin log. So that's essentially the idea. Then we monitor the new master for 24 hours. If the new master is behaving abnormally, meaning the new buffer pool size giving you a response time that's not aligned with the predicted response time, okay, we can switch back to that new backup, which was the old master, which still has the old configuration. So everything's supposed to work just fine. So that's essentially the idea. If the new master node, which was the old backup node, after adjustment, works just fine in this 24-hour period, then at that point, we go ahead and adjust the new backup, which was the old master node as well. So there are some experiments. So as I said, we have deployed this system over 10,000 database instances, which end up saving memory on a daily basis about 17%, which sounds like not a big number, but 17% leads to close to, as I mentioned, somewhere between 20 to 30 terabytes of memory for us, because we're huge. So 20 to 30 terabytes, if you look at the dollar cost, that's close to $1 million saving on a daily basis. Okay. And I want to show you, this is a real number from our production system. So we deployed this last year around October 1st. October 1st is a special holiday in China, which is something similar to the Independence Day in the United States. And October 1st, the holiday goes about 7 days. So right before the holiday, we deployed this. We were really nervous, right? Because yes, you got the WebDB paper and all that, but how do you know this actually works? So we choose that 7-day holiday and we deploy it. As you can tell, the response time, this is the service level agreement across the board. And there are 3 instances, the 3 dots, after using this algorithm, actually exceeded the service level agreement requirement. And QPS stayed relatively similar, except in the holiday period, as you can see, there's a significant drop, as you can tell. And if you look at the miss ratio, yes, after the adjustment, miss ratio goes up, of course, because we're trying to save memory. However, the key observation is miss ratio goes up does not necessarily mean your response time will be so bad that it will exceed the service level agreement. Part of the reason is when you initially set up your buffer size, you are being very conservative. You want to make sure your service level agreement is never going to be a problem. So you set up your buffer pool size in a really conservative fashion, so there is indeed a fairly big room for you to adjust and save. Okay, so that's essentially the intuition. And CPU, more or less the same. And I/O rate, as you can tell clearly, I/O has gone up after we deploy this automation algorithm. But the whole point is, if it goes up so bad, this adjustment will kick in and adjust the buffer. So it's not a one-way traffic. Adjust the memory down, it could adjust the memory up as well. So that's essentially the idea. And this shows you numbers from 10 real instances. As you can tell, there's only one instance where after we do the adjustment, the response time is super big compared to the doing the smart tuning before. We actually zoom into this instance, look at what happens. What happened in that instance is really interesting, is that, yes, the QPS of that instance is high, but there is one query is taking up all the resources. There's one query taking up all the resources. So if you do any adjustment not aligned with that one single query's pattern, it's going to be super negatively affected. So this actually is a really interesting observation for the future work to follow, which is, okay, machine learning and this general principle is really good at figuring out the pattern and principle for the crowd. But if there is a one elephant in the room, then whatever you do might not work. If there's one elephant in the room, then you are doomed. We don't have a good answer to this, and I hope the community can look into this. And if you do any sort of self-tuning, you do have to keep this in mind. That's one lesson we learned from this. Okay. So some of the concluding remarks and future work. So in addition to tune the buffer size, we are doing a lot of other things like cache preloading and multiple parameter tuning, pretty much like what Andy mentioned in his auto-tune paper. So we are trying to scale this out, branch this out to do not just buffer size tuning, but to many other parameter tunings. And in addition to that, so this is the big architecture we are currently developing. So at the bottom, we're using we have different type of database systems, right? PoloDB, MySQL, NoSQL, MongoDB, and so on and so forth. And on top of that, just like I mentioned, we use Kafka, Spark Streaming, and Flink to build a pipeline to collect performance data in real time, and using streaming processing engine to train our models. And then there's an action scheduler and action executor. Those modules, I have mentioned those in my talk, right? But we are trying to abstract them out to do not just buffer tuning, to do many other things. Then on top of that is all the things I have mentioned, right? Like automatic tuning, backup, high availability, and so on and so forth. Then to the user, they see this kind of features, right? Slow SQL identification, index recommendation, buffer size tuning, and things like that. So I showed this slide earlier in my talk, but I want to end my talk with this particular slide. Some of the problem we're working on right now. So of course, this is a big part of what we do. And then we are actively doing hot code separations and Cloud Bench, as I mentioned, anomaly detection, natural language to SQL. And over here, I want to mention one thing that we have deployed to production, and we are writing a paper to talk about that as well, which is not we look at index recommendation, but we haven't picked up a good strategy for that yet in production environment. So we did another thing. We did something called auto sharding. So you know, in share nothing database systems, like in HiStore, for example, which is later grow into a commercial company like VolDB, right? In share nothing or Google Spanner. One thing you need to do is to do sharding of your records into different shards or into different partitions. Traditional wisdom is to use a hash function, either hash by value or hash by range. But neither is ideal, because initially you can get an ideal partition of your workload so that transactions are perfectly partitionable, so that you reduce the percentage of distributed commits by a large degree. We all know distributed commit is the enemy of distributed database systems. If you have distributed commit in our experiments, more than 5% or 10% of distributed commits, your TPS is essentially throttled to almost zero, right? So what we want to do is to use a machine learning strategy to do the sharding intelligently, rather than relying on a static hash function to do it. We call that auto sharding. And we have seen very good results, which we will report hopefully later this year. With that, I conclude my talk, and thank you all for your attention. I'm happy to take any question you have.
Thank you very much. We have time for some questions. The microphone.
Yeah, I have a simple question. So for all this performance tuned database, do they run on the dedicated cluster in the cloud? Do they share the results with other systems?
You are saying whether the model itself, the training is offline.
Whether so basically you have the database instance running virtual machines, I assume.
Yes.
And to these virtual machines share with other tenants.
So there are two parts to my response, right? One is the training is offline, right? So we can do it on any cluster, right? The model itself is very lightweight and is deployed in the database platform as a service. In our database it's essentially become part of our database as a platform.
So my concern is like if you share hardware with other tenants, will interfere with the results container from other tenants, create noise to your model prediction.
But customers do not. Note that in the cloud scenario, customers pay for the resource of their instance. They don't, the database as a platform, the service itself, the control platform itself is sort of come at a free cost to the customer, right? Any cloud provider, they will have a DB pass. And customer only pay for the resources used for their instance. We are not taking any resource away from that, right?
Yeah,
okay.
Hey, I had a quick question
Yeah, go ahead.
the benefits of this model. So have you been able to figure out if the model can be extended to like CPU usage and disk usage? I know you mentioned that memory is the most expensive thing, and that's where some of the focus has been. But have you explored and had any success around like CPU consumption, maybe background threads or other entities, and also disk space usage?
Yes, in fact, in another product, which I didn't have time to go through, we call slow SQL identification. We want to identify slow SQL running anywhere in any of the instances we have. In those cases, the root cause for a slow SQL could be I/O bound. It could also be CPU bound. So for the latter, you need to look at other metrics holistically, rather than just looking at memory size. But in this case, I show the motivation, like for most of the instances we have, they are I/O intensive, right? So figuring out the hit ratio relation between response time is good enough.
So have you implemented schemes for?
We are in, the slow SQL product is work in progress. We have implemented that as well, but it's not in the production level yet, not like this. Okay.
Thank you.
All right. Thank you.
Thank you very much for the nice presentation. Really enjoy it.
Could you lower the mic so I can hear you?
Okay, I do have a question. So when you mentioned offline training, you mentioned for the few minutes, maybe the PPS or things won't change that much, so that you can do your predicted response time. But actually, in real case, like say for the single day promotion, like within that second, you have a large change. So do you have any heuristics for this?
Okay, very good question. So this works for day-to-day operations. Of course, it will be super challenging to try this out at the single stage case, right? Because in the single stage, the workload is really volatile. It's super volatile. Any pre-trained model will not work in that case. So this works for day-to-day operation where we do have regularity in the system. Does that make sense?
So if from a traffic pattern perspective, I think people are more likely to go shopping in the evening, like after they come back from work. And then from say for the last 24-hour traffic pattern, you might see pretty different patterns. Do you have any?
The training workload is collected over a long period of time. It's not just a few minutes.
Okay, got it.
Does that make sense? The prediction, of course, look at a short window.
All right, thank you again for the presentation.
Okay, thank you.